Okay, so let's start with the second lecture.
Okay. So let me recap what was the setting. We had a compact metric space with distance d and with at least 2 points. And together we had on it a semi-metric phi on x. So a semi-metric is a continuous. It's a function defined on pairs of points in x, such that phi xx is 0. And the second thing is that we have to satisfy the triangle inequality, but since it's not symmetric, the order is important. Okay? Now, because of the second thing, we have phi xy plus phi yx is larger than phi xx, which is 0. So this phi symmetrized is non-negative everywhere. And it's also, of course, a semi-metric. Okay. And phi max, which is the maximum of phi yx and phi xy, is also non-negative because the sum is not negative. Okay. And again, now these are two continuous semi-metrics which are non-negative. Okay, we define the notion of phi subsolution. Okay, so it's given by function is a phi subsolution if uy minus ux is less than phi xy. Okay, as I said, this is like the function which are Lipschitz for phi with constant one. Okay, it's equivalent, of course, to this inequality. This one is a little bit better to use because if you take inf, it can be minus infinity, or sup, it can be plus infinity, but it will still be satisfied. Okay? So these are the properties we showed for phi subsolution. So the family of phi subsolution is S sub phi. It's a continuous, equicontinuous family because, in fact, for any one of these subsolution, okay, we have uy minus ux is less than phi max of xy, okay, and phi max is continuous and 0 on the diagonal, so that gives us the equicontinuity. It's stable under pointwise convergence. Okay, this is because of the inequality. Maybe let me read it. So this is a definition of subsolution. So it's stable under pointwise convergence, this condition. It's also stable by taking convex combination. Now and you can also add a constant, you remain in the subsolution. And it's stable by sup and inf, provided the inf or the sup are not identically minus infinity. Okay, so the inf will satisfy the same inequality. And this is because phi is finite. If the inf is minus infinity at one point, it's minus infinity everywhere. And same thing for the sum. And once it is finite at one point and hence finite everywhere, it's a subsolution because it's an inequality. Now, the two functions we can get subsolution easily from phi. We fix the first variable, then as a function of the second variable, it's a subsolution. And if we want to fix the second variable, you have to put a minus sign to get subsolution. Okay. Now, we then define the concatenated costs for eta positive, non-negative, I should say. I allow eta equals 0. And in the following way, the chain is a sequence of points with at least 2 points. Okay. We can introduce the phi cost of the chain Okay, and the length, the concatenated length, in the following way: the phi cost of the chain, C sub phi, x0, xn, is the sum of phi at two consecutive occurrences of xi, and because of the triangle inequality, it's always bigger than phi of x0, xn. And for the length, we can do the same thing. Okay, but with d instead of phi. So the concatenated costs are then defined by phi eta of xy is the infimum of the cost of all chains going from x to y, but with lengths larger than eta. Okay? And this is why we need 2 points to be able to find chains of arbitrarily big length. If it's only 1 point, it doesn't work. Okay? And of course, this is always larger than phi of x. And we remark that because the distance from z to z and the phi of z to z is 0, when we have a chain, okay, when we compute the infimum, we can only consider chains that satisfy that two consecutive terms are not equal, because if they are equal, we can drop them, except we have to be a little bit careful. You still want to have a chain, so you need to have at least 3 points. So the only case where you cannot drop is x. So you have to add it. Okay. Now, I'm going to give the property of the concatenated costs, and they satisfy. Well, if you compute the concatenated cost for 0, you just get phi again. If there is no condition on the chain that you use, you get the one which gives you the smallest number. And of course, from the definition, the higher eta prime, the less chains you have to take the inf. You have less chains of which to take the inf. So you just have the inequality. And you have a triangle inequality, but with, so phi eta plus eta prime xc is less than phi eta xy plus phi eta prime yc. This is like a, I don't know, if convolution semi-group or something, almost not semi-group because it's less than equal to, but it's of that type. Okay, and phi eta of xy is phi of xy for all xy and all eta such that eta is less than the distance from x to y. Okay, and the family of concatenated cost is equicontinuous. We have this inequality, phi eta xy minus phi eta x prime y prime is less than phi max xx prime plus phi max y prime. So phi max is the symmetrized cost by taking the max of phi of xy and phi. Okay. So this implies the equicontinuity because this is phi max is 0 along the diagonals and is continuous. Now, one follows easily from the definition of phi eta. Okay, because the larger eta, the less change you have on which you take the inf. Okay, so that give you this one, and for phi 0 equal phi, all the phi eta of xy are larger than phi of xy, as we have seen, because all the concatenated costs larger than that. But for eta equals 0, the chain satisfies the length from x to y is not negative, so it's part of the chain. So this is a chain on which you have to take, among which you have to take the inf also. The inf, you have to take the inf including for this chain, so you get x. Okay. Now we want to prove this kind of triangle inequality, but this is quite easy. And the chain psi prime such that psi ends where psi prime starts, then you can put the two chains together. Okay, it's a concatenated chain. Okay, here you just take this as one point. Okay, and now if you compute the cost, you are going to find the sum of the cost. And if you compute the length, you are going to find the sum of the length. Okay. And therefore, if you take a chain that is almost equal to phi x, phi eta of xy, and the chain that is almost equal to phi of eta prime yz, then you take the concatenated chain and one will be this. Okay. Now, this one is the fact that if you look at the chain here xy, when eta is less than the distance of xy, this chain is admissible with length larger than eta. So in the inf, you have to take into account this. And since you know that phi of xy is less than phi eta of xy, whatever situation, then they have to be equal in that case. Okay. So, okay, the second part of 4 was this one here. Okay. The inequality, which, as I said, implies the equicontiguity. So this is what I have. Now, fix eta, non-negative, and suppose you have x, y, x prime, y prime in x. So you can look at phi eta of xy. So this is the kind of trick you will play all the time. It's phi eta plus 0. Okay, but then you can use a triangle inequality. But phi 0 is 5. So you end up with phi eta of xy is less than phi eta of xy prime plus phi eta phi of y prime y. Okay, so we just obtain this inequality. That's what I just told you. And we can get also phi eta of xy prime is less than phi 0 of xx prime plus phi eta in the same way, okay? But here we write eta as 0 plus eta instead of eta plus 0. And we get that, okay? So we combine the two inequalities. And we conclude that phi eta of xy is less than phi of xx prime plus phi eta of x prime y prime, okay? Okay, so because phi of CD prime is less than phi max, we get from this inequality this one. And this one is symmetric and xx prime and y prime. So you can obtain with absolute value inequality. Okay. So let me compute the concatenated cost for some of these 2 points. Remember, we defined if we have a continuous function from x into r, we define the concatenated, sorry, the cost u hat we define the cost you had. Okay, you had xy, also semi-metric, I should say, as u of y minus u of x. Now, if we have a chain and we compute the cost for u hat of the chain, we just find u of xn minus u of x. Okay. So this implies that u eta of xy is u y minus ux, because the cost of the chain of any length is independent of the chain. Now we can take as semi-metric d itself. So if we just compute the cost for this one, we get the length. Okay, we put c phi here, t is phi, but it gives you also the length of the chain. And of course, phi eta of xy is the inf of the c0 of x0 xn for length larger than eta. So it's the same as the inf of the length for length larger than eta. So it's larger than eta. Okay. And I don't know if that it is eta. I mean, this you really think of a finite set. Okay. The sum of the lengths can take only, I mean, some values are not taken as sums by, okay, by the distances of. Now, if I fix alpha, as I said, t to the power alpha is a distance defining the topology of the metric space. So we can take as semi-metric d, and as distance d alpha. In that case, the cost is just the sum of the distances, and the length is the sum of the distances to the power alpha. Okay? Because the distance on the space is given by d to the power alpha. Now we will show that for x in x not isolated, we have phi eta of xx equals 0 all the time. Okay. If the point is isolated, for example, then if it's only one in a ball of radius epsilon, okay, if you have no other point, okay, so if you want to get a chain of length eta, you have to jump here. So if phi, or point here to a point outside, is bounded below by some non-zero constant, this cannot be. Okay, so you have to do it. But if it's not isolated, it's going to work. So if x is not isolated, we can find a sequence xn, okay, such that the distance n from x to xn is strictly positive and goes to 0. Okay. Now, for a given eta, because Tn is positive, we can pick the smallest integer, non-negative integer, such that Mn Tn to the power alpha is larger than eta. Okay? Now, because it's smallest, the one before had to satisfy the opposite inequality. Okay? So this one is at least 1, of course, okay, because eta is positive, and therefore this one is at least 0, so it's still positive. Or non-negative. Okay, so the second equation bounds Mn. Find the bound for Mn, okay, by Mn is less than eta plus Tn to the power alpha divided by T alpha. Okay, now we consider the chain which goes from x. So we fix n. We are going to consider a chain of length, with 2 Mn plus 1 element, okay, because we start at 0. And we do it like that. We start at x, then go to xn, come back to x, go back to xn, etc., till we come back to x after 2mn steps. Okay, so this is this chain. So if this chain, it starts at x and ends at x, and what is the length for the alpha of this chain? Okay, it's a sum from I equals 0 to 2m n minus 1 of the distance from, well, I shouldn't have called it xi, but okay, it's not this xn. It's a chain, and it's a lab link of this chain. Oh, I should put a del tilde there. It's distance from xi tilde to xi tilde to xi plus 1 tilde. Okay, let me correct that. Okay. So, because all the distances between two consecutive points are T alpha n, we get that it's 2mn T alpha n, so it's larger than 2 eta. Okay. Now, what about the cost associated to D? Again, here it's a tilde. Now, it's the distance between the two, so it's Tn, and then we get 2mn Tn, but we bound Tmn above, and so we get in the end 2 Tn to the power minus 1 minus alpha eta plus T alpha. Okay. Now, on this inequality, because the cost is always non-negative in that case, the distance is non-negative. Okay. And it has to go to 0 when n goes to infinity. Okay. So the chain starts at x and ends at x. Each one of these chains, it's of length larger than 2 eta, okay? And the costs go to 0. That tells me that the eta concatenated chain corresponding to D, which I took as phi, from x to x, which is of course non-negative because everything is non-negative, is less than the infimum, which is 0, so it has to be 0. Now, I still keep x isolated, not isolated, and then I can compute the concatenated cost for all other points with x. Okay. So dxy is less than d eta of xy because it's increasing. Again, we play the same trick. D eta plus 0, so it's less than d eta xx plus d0 of xy. Okay. So this is d eta of xx, but d0 is dxy, but this is 0, and so this is one is just dx. Okay. So this is provided x or y are not isolated. Okay, now let me come to the pairs barrier. So we have the concatenated cost. Eta maps to phi eta xy is non-decreasing, so there is a limit as eta go to infinity, which is the sum. Okay. This is exactly the pairs barrier. Okay, it's the sum of the concatenated cost. Now, what are the properties of the pairs barrier? Of course, it's larger than phi eta. So it's larger than phi. And in particular, phi infinity of xx is larger than phi xx. So it's non-negative. It satisfies mixed triangle inequalities. Okay. And therefore, if it satisfies this inequality, because phi is less than phi infinity, it satisfies the triangle inequality. Okay. And moreover, we have either phi infinity is plus infinity everywhere, or phi infinity is everywhere final. And the pair barrier is continuous because it satisfies, and here it's not phi infinity, it's phi max. It satisfies the same inequality as the phi eta, as you can suspect, okay, because it's a limit. Okay, let me just do the proof again. So it's the first inequality, as I said, is because eta maps to phi eta of xy is increasing. And now I want to prove the second one, the mixed triangle inequality. So I just have to prove this one and this one. We'll prove this one and the other ones analogous. And the triangle inequality follows, of course, because phi is less than phi infinity. Now, again, we do phi eta of xz is equal to phi eta plus 0 of xz. We use that it is less than phi eta xy plus phi 0 of yx. So this is phi of yz. Okay, phi 0 is phi. So we get the first inequality. This one. Okay, when we let eta go to infinity. Okay. Now, the other one is similar, and the triangle inequality follows. Now, phi infinity is either plus infinity everywhere or is finite everywhere. Okay, it's because here phi xy is finite. So if it's plus infinity somewhere, it's plus infinity everywhere. Okay. And because it's a sop, it cannot be minus infinity. It cannot be plus infinity. If there is a problem. Okay, and if it's finite everywhere, okay. If it's finite at one point, then it's finite everywhere because phi is finite. Now, this thing here follows, as I say, the inequality on phi infinity follows from the one we established for eta by letting eta go to plus infinity. Okay. Okay. Now we compute the pairs barrier for some semi-metrics in some of the examples. Okay, so we start with the example where we took as cost q hat from where u is a continuous function. We showed that u hat eta is u for all eta, so the pairs barrier is also equal to u hat. If we take phi equal d, we have showed that phi eta is larger than eta everywhere, so the pair barrier is plus infinity, identically. If we take alpha in 0, 1, we show that d eta equals d if x has no isolated point. Okay. So the pairs barrier is d. So now let me come to the Aubry set. Once we have the pairs barrier, the Aubry set is defined as a set where phi infinity of xx equals 0. So of course, the Aubry set can be empty in case phi infinity is plus infinity identically. Okay, but we will show that if phi infinity is not identically plus infinity, we will show that the Aubry set is not empty. Okay, so it's not like a definition where it's always empty, but it's always closed because phi infinity is continuous. And for a given statement, so I'm going to show first some useful statement which says that I don't have to go to phi infinity to check that the point is in the Aubry set. So I have three equivalent statements: x is the Aubry set, which means phi infinity of x is 0. There exists some eta positive such that phi eta of xx equals 0. And the last one is for all eta, we have phi eta of xx equals 0. Okay? So 1 implies 3, okay, because this is phi of xx is less than phi eta of xx is less than phi infinity of xx. So if x is in the Aubry set, this is 0, so you have 3. 3 implies 2, of course. And it remains to show that two implies 1. If we have 2, if for some eta positive, so 0, of course, is not allowed because every point satisfies phi 0 of xx equals 0, then x is in the Aubry set, which is phi infinity of xx equals 0. Now, suppose phi eta xx is 0 for some eta. Well, we can just now take n eta, and by induction, so we know that this is always non-negative, okay, because it's larger than phi xx. So this is less by the triangle inequality, phi eta of xx plus phi n minus 1 eta of xx. So this is 0, so it's less than phi n minus 1. So we go up to phi eta of xx, and we get 0. So it's always 0, but then the limit as n goes to infinity of this subsequence goes to 0, but the sequence converge. The limit for all eta prime here exists, so it has to be the same. So we get that it is 0. And this will imply that if either x or y is in the Aubry set, then the Peyer's barrier is equal to phi. Again, all we have to show in this case is that phi infinity of xy is less than phi of xy. Okay? Because we have the inequality here. So suppose, for example, that x is in the Aubry set, that phi eta of xx is 0, and again, we play the same stupid game. Phi eta of xy is equal to phi eta plus 0 of xy, and then this is less than phi eta xx plus phi of xy. Okay, for every eta, so we get our result by taking the soup over all eta. The case y is in the Aubry set is similar. Now, let me compute the Aubry set for some of the already given example. Okay. So we start with this one. U is a continuous function, the semi-metric U hat. Well, we showed that U infinity is U hat, okay? And therefore, for every x, we have U hat infinity of xx is equal to ux minus ux, which is 0, okay? So every point is in the Aubry set. Okay. In the case where we take D as semi-metric, we showed that the Peyer's barrier was identically plus infinity, so it's empty. The Aubry set is empty. Now, when we took alpha in 0, 1, the metric space is X d alpha, and the semi-metric is D. We showed that phi infinity of XX is 0 if X has no isolated point. Okay, so the Aubrey set is again the rule of X. Okay, and now I come to the theorem. The Aubrey set is non-empty if and only if the pairs barrier phi infinity is everywhere finite. Now, of course, if A phi is not empty, because phi infinity of xx is 0 for x in A5, it's finite at some point. Phi infinity is a pair of points, so it's finite everywhere. Now, the fact that the finiteness of phi infinity implies A phi is not empty is a corollary of the next theorem. If the pairs barrier is finite, everywhere, of course, then for every pair of points, there exists a z in A phi such that, so z in the Aubrey set, such that phi infinity of xy is phi infinity of xz plus phi infinity of xy. And in fact, it's because we showed, because z in the Aubrey set, this is also phi. Okay. So I need to prove that. What does it, how do I compute phi infinity of xy? I have to take the limit of the phi eta for eta going to infinity, and then I have to take a chain approximating each phi eta. So in fact, because I can find a subsequence of chains, okay, psi n is the name of the chain, so it has mn points starting at x and ending at y, such that the length goes to plus infinity and the cost goes to phi infinity of xy, okay, from the definition. And now, let me just, I claim that for eta positive and every epsilon, for all n large enough, I can find two indices, Gn, Kn, okay, such that, well, Jn is less than Kn, so they are distinct. The distance between xn Jn and xn Kn is less than epsilon, and the cost of psi n is larger than the phi eta going from x to xn Gn, then going from xn Gn to xn Kn, plus going from nkn to y. Okay. Before giving the proof formally, or maybe not giving it, it's in the beamer, so it's a little bit long, but the idea is quite simple. Once you write down the details, it takes time. So you have this chain, the lengths go to infinity. Okay? So because the lengths go to infinity and the distance on the compact space is bounded, the number of points go to infinity. Okay? So you have this, so you have these points. So I'll try to write with the left hand, I can't use my right hand. So you have these points, x0, n, and then you have x, n, ln, okay, let me try again, maybe a little bit slow. So you have the point x0, n, you have the chain of points. Okay. Now, when n goes to infinity, the number of points go to infinity, and the length of the chain goes to infinity. Okay? So that means that I can find intermediary points here. Consecutive one is eta, because the length for when n goes to infinity, the length goes to infinity, eta is fixed. So that means that I can write my chain as concatenated chains, okay, of lengths which are at least eta. But the number of points I have here goes to infinity. And of course, I can keep on doing that, on constructing this chain till I reach the point where the sum of the remaining distances is strictly less than eta. Okay. So I need to have a lot of points there. Intermediary point, as n go to infinity, the number of points has to go to infinity. But I am in a compact space, so two of them have to be in the same ball. Okay, and this is exactly what I need, because then if this one and this one are in the same ball, here the length of the chain is larger than eta, so this is the cost is larger than phi eta. Same thing here and same thing here. It's exactly the same. Okay, so let me try to write down formally the things, and if it gets confused, you can read it. But the idea is simple. So we can cover the subset by a finite family of balls, and epsilon of them, or radius n epsilon over 2. So for each n, we define by induction a finite strictly increasing sequence, okay, where at each step, if INK is defined, INK plus 1 is the first index for which the chain between the piece of chain between IKN and IMK, sorry, and IMK plus 1 has length larger than n. Okay. So when does this stop? Okay, it stops at the n such that the sum from ANKN to n minus 1 of the distances of two consecutive points is strictly less than eta. Of course, this covers also the case where the last one would be n, because an empty sum of non-negative number, you have to take it as 0. Satisfied even by this case, okay? You don't have to worry about the exception. Okay, so we assume that we have taken enough points, so the last one satisfies the inequality. There is no way to go beyond that. Okay? Now, by the choice of IN K plus 1, this is the first time I am larger than epsilon, so if I do the sum with not the last step, it has to be strictly less. Okay? It's the first integer such that this is true. So the one before must be strictly less. Okay, so what is the difference between the two? It's just the distance between the two last terms. Okay, and this distance is smaller than the diameter d of x, backspace x. So in fact, here I subtracted from this sum something which is not as much as minus. So I get the inequality here with minus d subtracted. Okay. So if we sum these inequalities, we get q and eta minus q and d, sum from h equals 0 to in k minus 1. Okay. But this is less than the sum from h equals 0 to in Qn minus 1, but I can add more terms, the left term in the sequence, I get the length, so it's less than the length. Okay. So what we do, we just showed, this is part of the inequality, the left part. I rewrote it here. And I add to it the last term to get the full chain. Okay? So the last term are the one from INQN to n minus 1. Okay? And this is less than eta. So I get minus QNV plus the length of the chain is strictly less than Qn times eta. So Qn is larger than this number. Okay, just do the algebra. This goes to infinity, so Qn goes to infinity. So this is what I said. The number of terms there have to be bigger and bigger, the number of intermediary. Now, these points are contained in X, which is covered by a finite number and epsilon of wall of radius epsilon over 2. Okay? So that means that at least one of the ball has to contain Pn larger than Qn divided by n epsilon of this ball. You have Qn point that you have to put in n epsilon sets. One set must contain at least Qn over n epsilon point. And therefore, we can find a strictly increasing subsequence, okay, of the subsequence that we defined, okay, so that the X n I n k n L for L between 1 and P are all in the same ball. Okay. Pn of them, now, Pn also goes to infinity. And all I need, in fact, is to know that from after some time it is a. Okay. So this is a strictly increasing subsequence of the sequence that we defined before. So if you look at the term J plus 1 for this new subsequence, which is among the sequence here, it must be larger than this one. Okay? You have a increasing subsequence. Okay? For some increasing subsequence, so if you take the n term and jump to the n plus 1, in between there is one before. And therefore, if you take the sum here, okay, because this is bigger than this one, it's larger than this sum, which by the definition of the IN, okay, IN something, you have two consecutive terms here, so this is larger than eta. Okay, so what I get, so this is larger than eta, but I can estimate the cost of this piece of chain between IN KNQ and IN KNQ plus 1 minus 1, okay? And because of the triangular inequality, it's larger than the cost between the two endpoints, than phi between the two endpoints. Now, for n large enough, we have Pn larger than, so I can have at least 4 integers in that sequence. And what I do, I look at the first here, this is larger than eta. And then for the cost, therefore, this sum must be larger than phi eta of x0n, xn, kn, because it's a chain between these 2 points, okay, of concatenated lengths at least eta. And you do the same thing for the end, the last one, and it's also the last piece after 3. it's larger than eta, okay? And between the two, okay, and it has also to be the case between x, between the okay, between the all of them, between two consecutive one, and therefore this is exactly what I mean. I think it's confusing to look at it on the blackboard, but it's kind of straightforward. This is just the idea. Okay, and so this finishes the proof of the claim. Okay. So I had this chain whose length was going to infinity, psi n, whose cost was going to phi infinity of xy, and I broke them in intermediary points such that the cost is larger than phi eta of x, xn, jn, okay, of the intermediary point, but with phi h. Okay, we proved that claim. So let me finish the proof of the theorem. We first note that the equicontinuous family converges pointwise to phi infinity, so the convergence is uniform, okay, on the compact space. Now we pick a sequence of number eta p that go to plus infinity, and the sequence of number epsilon p going to 0. Now we use the claim with eta equals eta p and epsilon equal epsilon p. So the claim gives us, okay, a sequence np going to infinity such that endpoints C1n and C2n, okay, whose distance is less than epsilon p. So I have a long chain, so I have 2 points at distance, okay, and such that the cost of this chain is larger than phi eta p x z1 p z1p phi eta p z1p z2p plus phi eta p z2p y. I just applied the claim to the eta equal eta p and epsilon equal epsilon p. Okay, these 2 points are at distance epsilon p, which goes to 0. So I can extract sequence so they both converge to the same point z. So I can relabeling if needed or extracting. I can assume that both z1p and z2p converge to a point z in x. Okay. Now we just look at the inequality that defines z1p and z2p, and phi eta converges uniformly to infinity. Both z1p and z2p converges to z. Okay, and by construction, this chain, the cost for this chain goes to phi infinity. So we get phi infinity of xy in the limit. Okay, we can take the limit here because the convergence is uniform, is larger than phi infinity of xz plus phi infinity of zz plus phi infinity of xy. Now the converse inequality is valid because phi infinity satisfies the triangular inequality. And therefore, I get that. In fact, I have not used up to here that phi infinity is finite. All I said I could have done it even with phi infinity plus infinity identically. But what happened is that when phi infinity is finite, this has to be 0. Okay? But this has to be 0 means that in fact z is in the opposite. Okay? This has to be 0 because in fact, if I omit it, it's larger than these two terms, which by the triangular inequality is again larger than this one. So these two are equal, and because phi infinity is finite, then it has to be. And that's it for today.
That, any question? Actually, I have a stupid question about possible examples. So if you take a twist map of the cylinders, so you can get a family of these five of which apply these techniques to recover the original. So what would be phi? The generating function minus something?
Phi, it will be, so this is
The minimal action.
the minimal action. I mean, it depends at which minus, well, the cohomology.
No, but then you also want to make it 0. Right? Oh, yes, but S phi XX.
Yeah. Okay, but this is not the case in that. I agree.
Questions?
But the reset depends on the rotation number in this case. So
No, but I mean, this is okay. So this is a mimic for the continuous time case.
Yeah, so you consider a time-dependent Lagrangian associated.
And then you take the course.
Time one action.
No,
From max.
no, it's a minimal action for all the time. Okay, that's what it's a Manier potential. And then it's 0. Phi of XX is 0.
So if you take the time one action to be the cost, and
Then
then
it
minimize,
doesn't-
don't you get?
No. No, I mean, it doesn't apply to this case. Well, okay. Now we can modify. So my goal was at first to try to understand how to obtain the continuous time. Now, of course, you can play the other game. There are differences, you have to take them into account. But it's not covered by that. It's very important to have phi XX equals 0.
Yeah, no, exactly. That's fine.